The second half to lesson 6.5 introduces us to a new method for evaluating logarithms. We'll practice this method in simplifying, and then we'll utilize it in solving logarithmic equations. Let's define change of base. The change of base definition allows the use of a calculator to evaluate any logarithmic term, no matter what the base is, not just base 10. But we keep base 10 in mind with the definition. If you have the logarithm definition that's true, that stays in place, log base b of m, where m, b, and a are positive numbers and b and a do not equal 1. What this allows us to do is rewrite that logarithmic expression as a fraction. And within that fraction, we're going to convert our a to base 10. Now, it works for any base, but if we utilize base 10, we can plug it into our calculator. Here are just a couple of things to consider. If you have something that you can't use your power chart to evaluate, log base b of m, the m is going to always be in the numerator, and whatever your base was, that logarithm is going to be in the denominator. So here's an example of how this works. If you were asked to evaluate a logarithm, for instance, log base 4 of 19, that's kind of random. If we used our power chart, 4 to what power equals 19, we would say that wouldn't be possible. We can't evaluate it with an exact definition. But what we can do is apply the change of base property. If we convert to base 10, it'll look like this. Log base 10 of 19 divided by log base 10 of 4. Now, as you enter that into your calculator, make sure you're applying your parentheses. You would type log, and then it gives you a parenthesis on the left, 19. Make sure to close that parenthesis, and then divided by log parenthesis 4. And you should get to 4 decimal places, 2.12, and then it rounds up to 40. And we can check that. If you take 4 to the 2.1240 power, you get approximately 19. And this also works for ln. I know we're throwing a lot in this little definition right here, but if we tried ln 19, whoops, that's a little star right there, divided by ln 4, we would get approximately that same result. Down below, this allows us to simplify expressions. It says simplify each logarithmic expression to the nearest thousandth. So now that's only 3 decimal places. Up above, we did 4. So make sure that you're checking the directions. Log base 5 of 14. That means 5 to what power is 14? If we apply our change of base rule to convert to base 10, that would give us log of 14 divided by log of 5. Enter that into your calculator, and to the nearest thousandth, you should get approximately 1.640. Try the other two, B and C, and then press play, and we'll see if we get a match. All right, let's see how you did. In example B, log base 9 of 4 means 9 to what power equals 4? You should have gotten an answer that's less than 1 because 4 is smaller than 9. That means when you raise it to a power, it has to be a decimal that's between 0 and 1. I got approximately 0.631. In that last example, you maybe even knew this answer without even writing out the definition or plugging it in. Log base 6 of negative 12. That means you're raising 6 to some power and getting negative 12 as an answer. That doesn't work. If you wrote out the definition, log of negative 12 divided by log of 6, and tried to enter that in, you'd get error. Remember, you can take an exponent that's negative, but you can't take a logarithm of a negative number. Finally, let's use the information about change of base in solving equations, or to help us solve equations. When solving exponential equations, we know that step 1 is to isolate the base. The process is similar to what we did in topic 6a. Once you isolate the base, you want to convert to logarithmic form by looping. Again, everything we've done before. But in these examples, it won't be quite as easy as using just base 10 on your calculator or your power chart to solve. Now you're going to want to apply the change of base definition to solve. Let's look at just a couple of examples on the right. 4 to the x power is equal to 8. Now that sounds like something that should be on the power chart, and we're going to get an exact answer. But our process will apply the change of base. In step 1, we isolate the base. Looking at this problem, that's already done for us. The base is 4 because we're raising that to the x power. The second thing we'll do then is convert to logarithmic form by looping. And remember, when we convert to logarithmic form, we start off just by writing that prefix log. The base for our exponential equation is the base for our logarithm. From there, we loop. What are we taking the logarithm of? We're taking the logarithm of 8. And what does that equal? The exponent, which is x. Log base 4 of 8 equals x. Now that isn't exactly on our power chart, so what we'll do is use that change of base rule to manipulate it. To convert to base 10, letting us plug it in on our calculator, we'll apply log of 8 divided by log of 4. Now notice the logs don't cancel out. We have to type this into our calculator, keeping sure that our parentheses stay in check. Log of 8 divided by log 4 is exactly 1.5. So we're not even rounding to the nearest hundredth. I probably should have stated that in the directions more clearly. This is exactly 1.5. To check it, raise 4 to the 1.5 power. And yes, it equals exactly 8. Here's another example where we're going to have to do some approximating. Example B, 6 to the x power minus 14 is equal to 19. First, when we isolate our base, we have to figure out which one our base is. And our base is 6 because we're raising that to the x power. That means we'll move 14 over simply by adding it. 6 to the x power equals 19 plus 14, 33. Once your base is isolated, go to step 2. Convert to logarithmic form by looping. We start with that log prefix. If our base is 6, our logarithm base is also 6. What are we taking the logarithm of? 33. And the nice thing about this problem, what will it equal? It equals x. Now 6 and 36 would be power chart friendly, but 33 is a little bit smaller than that. Therefore, we'll apply our change of base rule. Log 33 divided by log 6 will equal x. If you enter that into your calculator, you're going to get approximately 1.95. Now, if you type in 6 to the 1.95 power, it's close to 33, but it's not exact. The further you round your decimal, the closer you will get when you check in your exponential statement. So just watch the directions on your Pearson assignment to make sure you're rounding to the appropriate value.